Hey everybody, welcome to another CS 302 assignment. For assignment 7, we're going to essentially implement a priority queue data structure, and we're going to implement this Resident Evil Mercenary leaderboard. So in Resident Evil 3, the original one for the PlayStation 1, the good one, not the terrible remake, when you beat the game, then there would be this mercenary mode, which was kind of an onslaught, but there was an actual end in the mercenary mode. But essentially, most of the time it was onslaught because I was never able to get to the very end of mercenary mode. But the way it worked was you would defeat various monsters in Raccoon City. You would get points, multiplier for each type of monster you would defeat. And of course, you can use those points to earn tokens to be able to buy various upgrades. Like you can have the infinite assault rifle and so forth. So we're going to have the same type of setup. So here we are. We're going to have essentially a set of mercenaries we're going to use. And then we have several different, I guess you can say, attributes that we can use to increase the rank of a mercenary. So essentially, throughout the mercenary mode, so this is going to be a different version of, you're going to have multiple mercenaries at one time fighting in Raccoon City. Each mercenary, may destroy a zombie, defeat those big spiders, drain demos, zombie dogs, hunters, and of course, Nemesis. And of course, if you rescue a civilian, you also get points. So for each of these will be a counter of some sort. How many zombies you defeated, how many spiders you defeated, and so forth, how many civilians you rescued. Each of these has a multiplier you want to apply, and you have to sum all those up. That's going to be the current score of a mercenary. And then, of course, the mercenary with the highest score is going to be at the front of the priority queue. So our priority queue we're going to implement is going to be not a min heap, but a max heap. Now, max heap is not much different from a min heap. So all a max heap really is that the parent node has to have a larger priority value than both children, basically. So it's really just you just essentially flip the inequality symbol, and that's it. So now that we have the mercenary, we're gonna of course define the mercenary type in more detail later on, but this is really the whole, I guess, the whole meat of the mercenary type. Let's go ahead and now discuss the priority queue data structure next. Okay, so I'm skipping ahead to the main for a quick second to help us understand how the priority queue class is going to work. So we define your priority queue in main. You're going to have a string to merc type priority queue. So your T1 will be a string and T2 will be merc type. Now merc type will be defined in a header file called merctype.h, and there it is. You have your class merc type. It's all public, so we're going to have our variables. So for each mercenary, these variables right here are going to simply track how many zombies this mercenary took out, how many spiders, how many drain demos, how many civilians saved, and so forth. You have to, of course, write your constructor. I'd recommend implementing a plus equal, but you of course can modify it. You could of course can implement a plus function instead, not plus equal. So it's up to you how you want to do this. So the header file from merc type, essentially you can of course can modify it how you wish. And you may want to also overload either less than or greater than. So I left this as a question mark because I'm not telling you which one to overload, but either less than or greater than, depending on how you're going to use this in your priority queue class. Because remember, it's going to be a max heap. So of course, the parent node has to be larger than both. And larger basically means which mercenary has a higher score. You compute the score by applying multipliers to each of these fields, and you sum them up for your this object. And then for your RHS object, you compare them. And of course, you can determine which merc would be higher in the leaderboard. So I'll leave that part open for right now. So let's go ahead and now go back and talk about our priority queue class. There's all of our text right there, but of course I'm just going to just, go over like I always do. So here we are. So we have we're going to include our unordered map right here. This is actually our PriorityQ.h file. So we have our map, and we're going to be using this map, and I'll go over in a little bit as to how it's going to work. We have our header guards as always. And then here we have our PriorityQ class. We have our T1 and T2, our key and priority type. And then we have this class defined within our PriorityQ class called priority type. We have our key and priority pair right there. And we have our constructors also if in case we wish to use them. So now in our PriorityQ class, we first have our heap array, which will be a dynamic one-dimensional array that's just going to be of type priority type. So we're going to have an array of this object essentially, because every element in your heap array will have a key priority pair. Now, capacity is going to tell us the max length of this heap array. And then size will tell us how many elements we currently have stored in our priority queue. Then, of course, we have our bubble up and bubble down functions. We pass an index. We want to bubble up from a certain position, and a bubble down, we pass in the index, bubble down from a certain position. So essentially, hopefully in your classes, you've covered these two functions, at least gone over just a visual trace out as to how it works, but very basic. So again, I mean, these are only difficult functions really are going to be just really bubble up and bubble down. So there we are. Then we have this map. And the purpose of this map is because, well, we may want to update a mercenary in our priority queue. So as we run our simulation, mercenary priorities essentially, as simulation continues, certain mercenaries might take out more zombies, more spiders, and their scores update while they're in the priority queue. We want to be able to update that mercenary, and this map is going to help us very quickly find where the mercenary is in our heap array, update that mercenary's priority, and then of course bubble up to its new position. But of course I will go over this visually in a little bit. So now let's look at our public members. We have our default constructor right here. It's going to set the size to 0, capacity to 10, and it's going to allocate an array of priority types to our heap array. Now, we're going to assign essentially size 0, capacity 10, and we're going to assign an array of length capacity plus 1 to heap array. And the reason why is because remember, index 0 for priority queues are typically our waste space. It's easier on the math if we use index 1 as our root element. So for that reason, index 0 is going to be a wasted spot. So we allocate capacity plus 1 elements to heap array to account for index 0 being a wasted spot. The destructor is right there. I already gave that to you. It's going to deallocate the heap array. Pretty simple. Pushback function is going to assign a new priority type element to the back of the priority queue and then bubble it up. So size tells you the end of your priority queue. So you want to create a new priority type object within our pushback function. This will be the key and the priority of this new element. You may want to assign it to index size plus 1. And then, of course, bubble up from index size, or index size plus 1. But you have to, of course, update the size variable once you assign it to our array. And then pop front, remember it takes the last element, so index size overrides the root with the index size element in the heap array, overrides index 1, and then bubbles down from index 1. Increase priority is going to look up and find this key in our heap array. It will update by adding this priority to that heap array element's priority field, and then bubble up from that index. Of course, I will cover these three functions in some detail momentarily. Get from priority, pretty simple. It returns the root node's priority field. And then get from key returns the root node's key field. Is empty, returns true if size is 0. It returns false if size is not 0, larger than 0. So in fact, these three functions are one-liners, so I could have implemented them here in this header file for you, but I guess I didn't. But they're really one-line functions, so very simple. So anyway, that's the preliminary of our class. Let's go ahead and now sort of in more detail, go over the pushback, pop front, and increase priority functions, which will help us out, help us understand what's going on. And then, of course, then we can go over like the main and go over the input and what the simulation is going to be. So here we are. So let's suppose we define our PriorityQ class, or sorry, PriorityQ type like this, a string to merc type object. So here's our heap array, and then our size will be 0, capacity will be 10, but remember the array is set to size 11 because index 0 is not even drawn here, but index 0 does exist, but it's not going to be considered. So the capacity would be actually 10 plus 1, 11 in reality here. So let's go ahead and go over how do we insert into our priority queue. So here is this content right here. Suppose in main, we just create a object called merc type m, and we set the spider's counter to be 3, let's suppose. And I want to push back a mercenary. I'm going to push back Carlos and an M. So of course we don't want to have a cruel Carlosless world. A very cheesy line from the Resident Evil 3 remake, but I gotta be honest, that was my favorite line in the game. I just loved that. It was cheesy, but I can relate to Carlos right there. So anyway, so right here we do a pushback. We pass in Carlos and we pass in mercenary object. So we're going to essentially, in the pushback function, we're going to increment our size by 1, and we're going to assign our new mercenary right here to index 1. So we're going to have Carlos right here. And of course, we're going to have that object, that merc type object will be right here. This object is going to contain the zombies will be 0, spiders will be 3, nemesis will be 0, and so forth. So this is going to be a complete object set. T2 type is going to be a merc type. So this is going to be your merc type object right there. And of course, you then be bubble up from index 1, and nothing is going to actually happen. And of course, we can add more elements into our priority queue by calling pushback a few more times. Let me go ahead and just do that right here. So suppose I were to, let's say, redefine, I want to have m dot spiders, maybe I'll have this one be 2, and m dot zombies, I'll have it as like, I don't know, 7. I'm going to insert another mercenary into my priority queue. So I guess it makes sense. I'll just use Jill. Makes sense to have Jill like this. So in this case right here, we're going to assign Jill into index 1's key field, and this object is going to be assigned to index 2's priority field. So here's what's going to happen. We increment our size by 1 once again to make it 2, and we're going to write Jill right here, and we're going to store that object that we passed in, which is right here. That will be assigned to the priority field, like so. Then we have to then call bubble up from index 2, and I would believe that Jill would have a higher score, I would think. So then what would happen is you would have to then swap Carlos and Jill in my priority queue. I'm not going to draw that whole thing out, but you have to, of course, swap these. So the issue here is how do we actually, bubble up? How do we swap? What we're going to have to do is when we call bubble up, so for example, at this point, I would, right after internally, inside a pushback function internally, you would call bubble up and pass in size at the very end. So after we assign Jill to index size, or we first increment size by 1, and then assign Jill right there, you bubble up from size. So what's going to happen is we would essentially have to compare, so size currently is 2. We have to compare index 2 with index 1. We have to, of course, compute the parent. Remember, in your classes, I'd imagine you would have covered this. If you take the current index divided by 2, that will compute the parent index of a node. And you want to compare these. So, of course, you'd have heap array index 1 and heap array index 2. Now, here's the deal. You don't want to say dot priority dot zombies larger than heap array next to dot priority dot zombies and so forth. And the reason why you don't want to do that, because zombies is specific to the merc type, but the priority type is not known. Now in this case, okay, fine, we define our object here in main. We define our priority type to be merc type, but this is actually unknown. Internally in our class PriorityQ, we don't know what T1 and T2 are. So we don't know what the key type is. We don't know what the priority type is. So we can say dot priority dot zombies or dot nemesis or dot civilians. If we do that, it's specific to the type. So what if, let's say, in your in code grade, I create another main file and I actually have a string I have a string comma int priority queue. So I have a string for my key, an integer for my priority. If I try to do .zombies, it will cause a compiling error. So you have to make sure that you have to assume that you don't know what the T2 type is. So going back to the PDF right here, T2 can be anything. In our context, T2 is going to be a merc type, but we have to assume that we don't know that. So we have to just kind of pretend like we don't know what the T2 type is. So you have to be very generic. So what you want to do actually, if you want to compare the parent and child, you want to just simply take the priority field of heap array and then compare them to each other. Either you can use less than or you can use greater than. Either one is fine. But what you want to do is make sure for the merc type, you have to define that operator, because this operator right here is going to get called right here when we're doing our comparisons. When you're doing bubble up and bubble down, remember we have to compare the node to its parent or compare node to its children. You have to use this last integrated operator will be called to compare. So then therefore, what you want to do is make sure you implement, you can define more than one operator if you like for this class, and make sure you call the merc types operator, because in this case, priority in this context is going to be a merc type object. So you want to call its comparison operator to implement bubble up. And then of course, for bubble down, same idea. You would take the index size value, override it to index 1, decrement size by 1, and then bubble down from index 1. And then same idea, you have to, of course, compute your two children indices, determine which is your bigger child, and then compare that bigger child to the parent. But you want to always use the comparison operator, because the priority type, the priority type, as I keep trying to mention, is not known. So the last integrated operator is a good way to write this in a generic way, because now if priority is an integer type, the less than will work. If it's a merc type, as long as you define the merc type's operator less than or greater than, it'll also work. So it's going to work for any type as long as that operator is correctly overloaded. So I hope I didn't over explain that, but that's the idea. So that's how you want to think about the push back and pop front. Same idea. You have to use bubble up, bubble down, but the same method as explained in class. So now I want to go over, what about the update function? Or what about that unordered map that we had defined in our class? How is that going to be used? Let's go ahead and discuss that next. Okay, so for the, this is the item to PQ map. So suppose we did a bunch of pushbacks and we bubbled everything up, and this is the correct location. So Carlos has a larger value than both Jill and Ada, and Jill has a larger value than... I just realized right now how I actually skipped 5. Oof. Well, that's too bad. I guess I don't know what happened there, but anyway, not important. So I'll put 5. I'll just fix it now then. So anyway, let me just quickly fix it. I want to stop the video now. At least I acknowledge this error, so that's good. I don't want to like to skip over. So it should be actually one more spot. It should be a 10th element right there, but not important. Okay, so suppose right here we have this setup. We have these elements inserted into our priority queue. We bubbled them up. And again, just to kind of recap, Carlos has a larger priority than both Jill and Ada. And Jill has a larger priority than both Leon and Ashley. So you can just assume that. So right here in our map, we want to map each key to the correct index in the heap array. So Carlos is at index 1, Ada is index 3, Leon index 4, Jill index 2, and Ashley index 5. So you want to, of course, have this because in our update function, so suppose somewhere down the line, down the road, let's say I were to do something like, I don't know, m dot, maybe I create another object, let's say. I call this maybe merc type. I'll call this maybe just m1, I suppose. And then m1 dot, if I can write a little better, that'd be fantastic. Zombies equal, let's say, 3. And I want to go ahead and update maybe Ada's zombie count. So I'm going to go ahead and say something like mercenaries dot update, I think it's called increase priority dot increase priority Ada, and I'll pass in M1. Okay. So in the increase priority function, we have to first find Ada. So we could linear search our heap array and then find Ada, but a better way would be, okay, I pass in the key into the increase priority function. I pass in Ada. In my map, I can look up Ada in constant time and returns the value 3. And that value 3 tells me that Ada is at index 3 in my heap array. So in constant time, I can find Ada. So now what I do, I take this, I pass an M1. I'm going to add that to Ada's current priority. So here's where we want to, of course, use either plus or plus equal function to increase the priority value. Because in this case right here, we create an object. We have zombies 3. This is going to, of course, add 3 to Ada's zombies field is going to be the result. So we have to pass in this object, and we call the plus equal function to update the priority field for Ada, and then bubble up index 3 because Ada may move up in the priority queue after this. So the purpose of this map is so we don't have to linearly search the heap array. This map will tell us where each element is. So of course we can use a bracket operator on that parameter. The items to PQ map returns a value, and that value can use that to index the element in our heap array. So of course you have to constantly update, because let's say, for example, when you bubble up and a swap has to happen. So suppose I were to update Ada. Let's say Ada's priority value will now become larger than Carlos's. We have to swap Ada and Carlos in a heap array. We have to also make sure we swap these values right here as well. So now Carlos will be at index 3 from now on. I have to swap Ada and Carlos's value also in the item to PQ map. So that way when we swap Carlos and Ada, we also swap the 1 and the 3 right here. So now we would have Ada's new location, index 1, and Carlos's new location, index 3. So that's kind of the bulk of it. So I don't want to really explain too much more. I want you to, of course, figure this out. But again, just try to make it as visual so you can see the problem or see how this works. But anyway, let's go ahead and now go over the input files provided. And then, of course, just go over a test run of this program. So you're given 2 input files for your program. The first one will be mercenaries.txt. And it's going to give you a list of all the mercenaries you're going to be using in our simulations. You have Carlos, Mikhail, Nikolai, Jill, Leon, Chris, Claire, Ada, Krauser, Luis, Wesker, Ethan, Heisenberg, and, of course, Lady Dimitrescu. So what we're going to first have to do in our main is read this file And of course, we're going to pass these two file names via command line arguments. So argv1 will contain the file called mercenary.txt. You can open an input file stream variable. You got to read all these in and push each of these one by one to your priority queue. Now, you're going to pass in for the priority type, you're going to pass in a default object. So all you have to do in main is just define a merc type object, which will use a constructor to set all zeros for all of the actual attributes of that priority type. And you just simply push back each element one by one. So you would just simply essentially read in Carlos, push back Carlos, comma, a default merc object. Then you would push back Mikhail, and then pass in a default merc type object. And then same thing for all these elements in your in this file. And then you're going to open up your simulation file. Here's one of them right here. And essentially, all you have to do is for every single line, you read an Ethan and then zombies and then 1. So what's going to happen is you read an Ethan. So what you're going to do is you're going to then create a merc type object, like a temporary one, and assign 1 to the zombies field, and then call the increase priority function, pass in Ethan, and pass in an object that contains 1 for the zombies field. It will update Ethan's zombies count, and of course it will cause a bubble up to happen in your priority queue. And then next line, you read in Claire, the name, then civilians, and then 10. So you have to, of course, then call the function increase priority, pass in Claire, and pass in an object that has 10 for its civilians amount. So maybe you can create a local variable called merc type local variable with all zeros, and of course assign the 10 for the civilians field, and then pass that object into the increase priority function. This will find Claire, increment her civilians count by 10, and of course potentially cause a bubble up. And then same thing. So for every single element in this file, you read in the name, and then of course you will just create a default, you create a local merc type object, have everything be 0 except for this one. You want to then set the drain demos to be 3, and then of course call the increase priority, pass in the key Ethan, and then pass an object that has 3 for its drain demos field. It's going to, of course, increment Ethan's drain demos count by 3, and of course then call the bubble up function. And that's sort of the idea, what you have to do. And at the very end, you want one by one, just pop each of the elements off your priority queue one by one, and output the name of the mercenary along with its final score, just by essentially you apply the multipliers onto each attribute and sum all of those up, and then display that to the screen, and of course the rank of that mercenary. So first element you pop off, that would be the first rank. The next element you pop off would be the second rank, and next one you pop off would be your third rank, and then so on and so forth. That's the idea. Let's go ahead and now demonstrate this program in our terminal. Okay, so before I go over the test run of the main file, I want to first show you this PQ test that I provided for you. It's also on CodeGrade as well. This is just to simply test out your PriorityQ class. So this one's going to be a PriorityQ object that's going to be a string for the key and an integer for the priority. So here's an example of how you want to make sure that in your PriorityQ class, your pushback, pop front, bubble up, bubble down, you don't want to do anything specific to the key or to the priority fields of each element of your heap array, because you don't know what the T2 or T1 types could possibly be. Or in this case, the T2 types could be int or it could be merc types. So you have to be careful to make sure your code works for either one. So in this context, we can think of integer would be a distance taken. So the racer with the furthest distance traveled the furthest, so that would be in first place. So we first push back all of our racers onto our priority queue with the respective distances. Then we increase each racer accordingly. Then at the end, we actually output the ranks. So we output the racer in order, in its order, in its rank order. So the very first racer on your priority queue would be in first place. After you pop it off, the next element at the root would be the first place among the remaining racers, which would really mean this racer is in second place. After you pop it off, the next racer would be in third place. So we constantly output the racer's name along with its priority or distance taken. We then remove it from the priority queue. The next largest one would move to the root position because the bubble down is going to cause the next biggest one to make its way to the root position. So to compile this, it would be g++, PriorityQ.cpp, and we have pq test.cpp. And then there we are. Now to come down to run this, we just do a.out. So what happens is Peach initially has the value 7, but if you notice in our increased priority, this is going to, of course, update Peach's value with 7 to the value of, well, we're going to add 11 to Peach's current value of 7 to give us 18. And Peach is at the root position of our priority queue. And then, of course, after you pop Peach off the priority queue, then Luigi with the value 14 is now going to be at the root position next. We then output Luigi and Luigi's priority, which is 14. We pop it off the priority queue, and then Donkey Kong will be our next biggest element we have. And of course, then we pop Donkey Kong, then Bowser, then Toad, Mario, and then Yoshi. So we, of course, can run this in our debugger as well to help us visualize this. So let's go ahead and do that. So I'm going to do g++-g PriorityQ CPP, and then of course we have pq test.cpp. Then I'll do gdb a.out. I'm going to go ahead and just run this, or I'm going to create a breakpoint on the main function and then run. So there we are. Let's go ahead and just run a few lines of code here. Let's go ahead and insert these racers onto our Mario Kart object. And then let's go ahead and now just output what's in our Mario Kart object. So I can do p for print, Mario Kart. So the capacity of this object is 10. The size will be 7. You have 7 elements you push into the priority queue. Heap arrays, dynamic arrays, it's not going to actually show anything. But luckily we have this onward map right here. It's going to kind of tell us where each racer is. So Yoshi's at index 7, Mario index 2, Toad index 3, and so forth. So this map is a very nice tool to help us debug as well, because it's going to kind of give us where each racer is. So this can help us with debugging. So if I wanted to simply output, say I want to output Luigi with its priority value. So right here I can see index 6 is where Luigi is. So I can say P and then Mario Kart dot heap array at index 6, since I know 6 is where Luigi is. And it's going to display the key at index 6 contains Luigi, and the priority contains the value 4, which is accurate. That's Luigi's value right there. We can see that. So it looks good. And of course, you can test it out with the other racers as well, but I'll leave it there for right now. So now let's go ahead and run line 21, which we're about to update Bowser's priority. So let's go ahead and first check out what's Bowser's priority currently in our priority queue. So Bowser is at index 5. So let's go ahead and just display that. So Bowser has priority 1 currently, and this is going to update Bowser's priority from 1. We're going to add 11 and set Bowser's priority now to be 12. Let's run that line of code. Let's go ahead and now output the priority, Mario Kart. And we can see Bowser's at index 2. And I think the reason why is because Donkey Kong and Bowser now both have the same value, both same priority of 12, because Bowser, we added 11 to Bowser. So Bowser had 1 plus 11 is 12. Donkey Kong, we initially had it at 12, so it won't bubble up over Donkey Kong because my priority queue is set up where if the parent is larger than or equal, then it's not going to actually swap. Let's go ahead and just check out and see if Bowser's priority is correctly updated. So Bowser at index 2, and there we are. The priority is now 12, and it bubbled all the way up to index 2. And let's go ahead and now run the rest of these lines of code. So now we're currently running Luigi. We're going to update Luigi's value of 10. Then we're going to update icon 1, and then Peach 11. Let's go ahead and now check out our PriorityQ again. Mario Kart. So Peach is at index 1 now, because index 1 has the highest value of 18. And of course, right here in our code, when you say Mario Kart get front key, it outputs Peach, and outputs Peach's priority. And displays it right here, Peach 18. Then we do pop front. So after pop front finishes, let's go ahead and check out our PriorityQ once again. So now our size is 6, not 7, because we just removed something. So remember what happens with pop front. Index 7, the end of our PriorityQ, overwrites index 1 and then bubbles down index 1. And then also, what I did was in my map, I actually removed Peach completely. It's very simple to remove. You can just call the erase function on your map, and it's going to just erase that element from your map. So I erased it as well. So now we don't have Peach anymore in my map. So Peach is no longer in my PriorityQ at all. And now Luigi is at index 1. So when I go ahead and say Mario Kart.get front key, it's going to get Luigi, and it's going to get Luigi's priority, which is, I believe, 14. And of course, once the size becomes 0, this empty function returns false, or sorry, returns true, I'm sorry, and then not of that true makes it false, which will break out of that while loop. So this is actually a very good test. If yours works on this, then your PriorityQ looks pretty good. And again, the same function will be applied on when you do the update function. You have to take whatever number you're passed and add that to your current priority. Now, you can do the same thing for merc type. As long as you overload the plus equal or plus operator for the merc type, you can, of course, add two merc types together to update the merc type priority. So literally, it's the same exact code you're going to have to use, but as long as you overload plus and plus equal for merc type, it should work just fine. So now for the for our program, for our main program. So to compile that, you would just do g++ PriorityQ CPP, and I have a main.cpp. And to run this, we want to first pass in our mercenaries file. So that's going to be our argv1 contains mercenaries. We can open up a file stream, pass in argv1, and read that entire mercenaries file, and then populate our PriorityQ. Then I'll pass in my simulation 01.txt. That'll be assigned to argv2. We're going to open up that file stream with this file, and then, of course, run that simulation, read each line, read the key, read in the type of attribute and the value, stored into a temporary object, passed it into the update, increase priority function. It will find that mercenary, add the object, the mercenary object, the merc type to the current one, and of course cause the bubble up, same as we have here for Mario Kart. Same idea, but it's wrapped around in these objects. And then of course, there we are. Now, I believe I might have missed this when I was going over this earlier. We want to, of course, always output whenever we have a new leader. So whenever you do a increased priority, something else might bubble up to the root potentially. So you want to have some variable defined in main that has the key of the current leader. And then of course, after every time you do increase priority, if a new element bubbled up to the root, you want to, of course, output this change, and of course, maybe reassign this key and priority to a separate variable. So you always kind of always know the new updated leader. And once you do your simulation file is done, you want to output the ranks. You want to first output Leon, or output essentially same. It's going to be the same exact like this. So this is kind of like your template for that. It's going to be the same concept. You want to output the key and the priority, except that the priority is going to be merc type. So you want to maybe get the priority value and of course store it into a temporary merc type, and of course add up, with the multipliers for each monster and output that result. A little extra work actually, but similar. They want to pop it off, and then next one will be clear. And this number right here is going to be a counter increments after every pop front. So there we are. Now, if you want to run this in a debugger, now I can't run a debugger here because it would expose my main program here in the video. But to debug this, you can do g++-g PriorityQ.cpp main.cpp. And of course, you can do a breakpoint on any file. You can do breakpoint on PriorityQ.cpp and then colon, whatever line you want to breakpoint on. You also can do break on main.cpp. I can do a line, let's say line 10 or something, I don't know, like that. Oh, oops, I made a mistake, sorry. gdb a.out first. Okay, now we can do that. So we can, of course, do a breakpoint on main.cpp on line, let's say 30 or something, I don't know. There we are. Now, if you want to run your debugger, you would do run, and right here you would go ahead and pass in mercenaries.txt, simulation1.txt, and you want to hit enter, and then it's going to, of course, feed in these two into your two argv1, argv2, and then it will stop on line 30, and of course you can, display the contents of your priority queue and see how things are updating. So anyway, hope this video did help you. So I guess that's it for now. Till next time, and of course, as always, happy coding.